So this is Algebra 1, Semester 2. It's the 4th unit called Exponential Functions. It's the 3rd lesson called Exponential Growth and Decay Practice. It's on creatormath.com under the Algebra 1 tab. You might have to Google creatormath.weebly.com to find the site. The instructions are copy the following problems into your composition book on the correct pages according to the table of contents with the notes for those pages from creatormath.com. I will try to show you how to find the notes. It's a little bit difficult. Here's the website name, creatormath.weebly.com. Google that. If you do, you should get to this homepage. On this homepage, should look like this. Any questions on the composition book, please scroll down, find the words composition book, and follow all the directions, watch all the videos, adhere to the turn-in dates, and put everything on the pages where they belong, including the notes, which we're going to go to now. We have to go to the tab of the course we're in, or the video we're making in this case. Here you will find all the notes, you'll find the problem sets, you'll find the videos on how to do the problem sets, as well as the page numbers where everything belongs in your composition book, and you will find the list of vocabulary for the entire school year. So if you're not getting 100% on your School G vocabulary practices, you may not know there's a complete PDF of every vocabulary word we will use through the entire school year. It is downloadable to your device and it is searchable. Just Google, how do I search a PDF on whatever kind of device you're using. It is a little bit different per device. Next, find the relevant semester we're in. In this case, this is the one we're on. Here comes next the table of contents. This is very important to the course, so that's why I ask you to put the entire table of contents on pages 2 through 6 of your composition book. Why is it so important? Because it lists all the page numbers that you're going to put everything on in the comp book, so that when I check it, at least I can find what you've got in there, right? Without searching around so much. So next we're going to do is find the unit we're in. So here it is, exponential functions. Then the lesson we're in, which is number 3 in this case. So exponential growth and decay page. Here are the page numbers where these notes go. Please don't take this video's word for it, but go look at the original table of contents on the website at the time you're viewing this. These page numbers probably will have changed. Here's the notes, the problem set, and the video solution will be linked right here when it's done. We're going to click Notes to take a look at what we're talking about for this lesson. Knock on wood, it usually pulls up in 2 times for me or less. This time it pulled up the first time. You should be able to expand the notes so that you can see them and put them on the correct pages in your composition book. So the important aspects of this is given a function f of x equals a times b power x. When a is greater than 0 and b is greater than 1, the function is an exponential growth function. So we're talking about 2 things, and this is the 3rd lesson in this set, so if this doesn't sound immediately familiar to you, make sure you're going in order for the lessons because they build on each other. So then it also talks about when a is greater than 0 and b is between 0 and 1, that would be like 0.5 or something like that, right? Would be between 0 and 1. The function is an exponential decay function. So we're going to look at 2 types, an exponential growth and an exponential decay function, and notice that they both have this generic format of a times b power x. This is a power symbol, otherwise known as a caret, like you use in English to squeeze something in. It means to raise b to the power x. Okay, let's see what we've got in here. So given a function, here's what we've got. A times b to the power t, right? Notice that b is 3 halves. 3 halves is 1.5, so 3 halves, which is greater than 1. Notice that a is 5, therefore it's an exponential growth function. If we just look back at this one where it said a is greater than 0 and b is between 0 and 1, it is and b is greater than 1, it is an exponential growth function. Hence this is an exponential growth function. Here's what the growth function curve looks like. We're going to look at that in the problem sets. So let's go ahead. Here's vocabulary that goes in your comp book. 3 dots means therefore. Here are the exponential growth and the exponential decay, etc. Okay, let's take a look at the problem set and see if we can work through a few. So let's go to the first problem. Determine whether the function represents an exponential growth or exponential decay. Identify the percent rate of change. Hint, use desmos.com to graph the function given. F of x equals a b to the caret x, where a is greater than 0. So here they even repeat the information from the notes, and here's what it is for an exponential decay. So let's look at the first one. It's right here. It says f of t Let me rewrite it so it's a little bit easier to see. F of t equals 5 times 3 halves raised to the power t. That's what this caret means here, okay? So this is in the format of, we said f of x beginning was a times b to the x power, right? And so right here, the b is 3 halves, which is 1.5. So that's between 0 and 1. So if we look right here, well, no, that's above. I keep saying that, but b is greater than 1 here at 1.5. And a here is 5, so it's greater than 0. Those two conditions apply. This is an exponential growth function. So we know we have an exponential growth. I don't like decay or decay. There's another growth here. Well, the way it works is the y-intercept or starting point of this function is 5 because a is 5 right here. How do we know this? Well, they told us to do something that we need to do. They said, go to desmos.com and graph this thing. Okay, let's let it load. Let's put in a function. And I'm going to literally type it like they did. Go to ABC and say f parentheses x and parentheses equals. So they said 5 times, let's use another parentheses, 3 divided by 2, or 3 halves, parentheses. No, I don't want the parentheses there. I want the parentheses there. Okay. Caret, or raised to the power of x. Okay, so the variable match. They use t and t. I'm going to use x and x because that's the typical xy. Notice that the exponential growth, we can tell it's exponential growth because that's what it looks like right there, and you're going to see that in a minute. But if we look at where it crosses the y-axis here, it's right at 5, 0, 5, right? So that is the beginning point, and so they say with y-intercept 5, that's our answer right here, exponential growth with y-intercept of 5, all right? With that said, let's see how repetitive these get. Here we go, f of t, let's rewrite it so it can be seen a little bit easier, is 25 times 9 over 10 raised to the power t. Well, 9 over 10 is between 0 and 1, that's 0.9. So here we have between 0 and 1 this condition. A is greater than 0, okay, this condition. So this is an exponential decay function. And notice our starting point is 25 here, so we can expect a y-intercept of 25. This one we should be able to graph more quickly. Let's go ahead and, where is it there? Let me see both, okay. Let's make this a 25. That's pretty easy to do. Make this a 9 over 10. We're just going to modify the one that's there. Put a 9 in here, okay, and hit home to find the graph. All right, come on. Here we go. So notice it's the exponential decay, which is a shrinking function, right? And notice where it crosses the y-intercept right here. Let's click it, 0, 25, right? So that matches up with exponential decay, y-intercept of 25. There we go. Okay, so here's our next function. F of t equals 80, 1.25. T. So, do we already know that it's greater than 1 for b right here. So I know it's exponential growth, right? Greater than 1. And a is greater than 0. Exponential growth, and I know it's passing through 80 because that's its starting point right there. Right? And I'm going to graph it, but this might be my last one because I'm starting to see the pattern. Remember, this is Algebra 1. So our exponential growth and decay is not very complicated. They're really getting us sort of used to the idea of what is exponential growth and decay, what does the graph look like, so that next year in Algebra 2 we can go into this a lot more deeply, and it won't be something brand new that students have seen. 1.25 to the x, home. Oh, it's kind of too much. Let's see where it's crossing here. Let's click here and here at 80, so that's exactly what we said it was. Exponential growth passing through the y-intercept of 80, right, which is the starting point here of 80. And we'll see that when we're going to do a few calculations involving finances, and that A right there term is the starting point. If, let's say, it's a loan, it's going to be the starting balance of the loan. So determine this function. Let's look at this one. F of t equals 16 times 1.3 caret t. or raised to the t power. So 1.3 is greater than 1, a is greater than 0. This is an exponential growth. Its starting point is 16. Piece of cake. And I might even skip the graphing just because I know what's going to happen. Let's go on to this one, which talks about finances. So we're going to invest $600. That's a starting place. So now if I'm talking about f of time, because $600 is an investment, time is what relates to investments. An investment pays 4% interest annually and is compounded semi-annually. Now that's a little bit complicated, but what this means is it's 4% interest per year annually, but it's compounded every 6 months or twice a year, right? So let's take a look at our options. Okay, let's take this one. Let's just consider all of them have a 600 here. Why? Because in our format of a times b raised to the power t, the a is the starting point of 600. That's where it's going to cross the y-intercept or the y-axis and form what is called the y-intercept. Now we're going to multiply by the interest rate, which is 1.02. Okay, so why is the interest rate 2%? Well, because it's 4% annually, and we're going to do everything on a semi-annual basis. So we're going to raise it to a 2t because there's 2 terms involved, and we're going to take the 4% and divide it by the 2 terms and get 2% per term. Okay, so 1.02 is the 2% because of this, because it's 4 divided by 2 terms. And it's 2 times terms because that's what takes it back to the annual basis. All right, so f of t equals 600 times 1.02 caret 2t right here. And just to, let's see if we can model this one. Let's put in 600 here. Okay, and let's put 1.02. And let's raise this to the power 2x. All right? Let's try to see this. Right here is where we intercept right here. See that? At 600. So that's exactly what we're talking about in terms of what we've done so far. Here we are at 600, 1.02 caret 2t. Right? And I believe they give us another one very much similar to this. And again, they're not going into the financial model very much at all. They're just sort of getting us used to the idea of the way, the format of this function of time equals a times b raised to the power t as an exponential growth or exponential decay function. All right, you invest $2,800. So f of t equals 2,800 is our starting point. What's the interest rate? It's 1% interest annually, but it's compounded semi-annually. So I know I'm going to have 2 times t here, because it's 2 terms happening in a year. And I'm going to take the interest and go back to the basis of how often it's compounding. I'm going to take 1 and divide it by 1% and divide it in half, which is going to be which is 0.5%. All right, so we start with 1 point instead of 0.005, instead of 0.1, which would be here. Split that in half and it becomes 0.5 raised to the 2t. All right, so f of t was 2,800 times 1.005 caret 2t. All right, and so we know our y-intercept is going to be 2,800, and we can graph that on desmos.com. All right, as you're going through these problem sets, let's look at the 3rd page before I go. Getting a little bit ahead of myself. All right, determine whether the function represents exponential growth or decay. Anything that goes like this, right? And notice it's even more extreme here depending on the function. It just goes straight up. This is an exponential growth. Whoops. Come on. There we go. My bad, you guys. So anything that goes up this way is an exponential growth. There it is there. And contrast that with what an exponential decay looks like. As you're moving left to right, this thing is shrinking all the way down to almost 0, right? And do you know that this heads towards 0 closer and closer and closer, yet never, ever reaches 0? So one of the cool features of these type of functions. So this is an exponential decay. So the big thing is, as you move left to right, it's decaying or reducing. As you move left to right, it's increasing or expanding. And this would be a virus curve, you guys. We all know virus curves now. We got it. Virus curves start out slow. Everybody starts getting sick. They start creeping up. And all of a sudden, they're like, everybody's sick in the entire world. so it just skyrockets to the moon. That's the idea of an acceleration or exponential curve. All right, so make sure you're matching up the title of this video with the problem set you're doing. This is Algebra 1, Semester 2. It's the 4th unit called Exponential Functions and the 3rd lesson called Exponential Growth and Decay Practice. It's on creatormath.com under the Algebra 1 tab. Hope this helps.